So this time around we're going to be looking at naming ionic compounds. Before we get into that, let's just look back over those chemical bonds. I'm not going to go through all these. Remember we talked about these before. But main thing is we're going to have those two types of bonds. We're going to have those ionic bonds and we're going to have those covalent bonds. And remember, with covalent or molecular compounds, those are going to be formed from nonmetals combining with nonmetals. That's where we get the covalent bonds from. Covalent bonds are sharing of electrons. With ionic compounds, that's going to be formed from a metal and a nonmetal coming together to form those ionic bonds. So ionic bonds are going to result from transfer of electrons between atoms. When we transfer electrons, we're going to end up with oppositely charged ions. All right, remember we talked about cations, we talked about anions. Cation is formed when an element loses electrons, and anion is formed when an element gains electrons. So that's what's going to happen here. So if we look at a neutral sodium atom, that neutral sodium atom loses an electron, it's going to form an Na+1 ion. But in order for that sodium to lose that electron, it has to lose that electron to something that's going to accept that electron. And that's where the chlorine comes in. So if the chlorine accepts that electron, it forms a Cl- ion. It has a -1 charge. So if we've got this Na+ and this Cl-, what's the force that's holding these ions together in an ionic compound? Well, that force is going to be an electrostatic attraction. Okay, so what causes the ionic bond to form? The main thing leading to the formation of these ionic bonds is because energy-wise, the ions are more stable than their neutral elements. So these neutral elements actually want to gain electrons, lose electrons to go to their ion forms because that's more stable for them. And then once they're in that ion form, that electrostatic attraction holds them together. Now this is just another picture showing pretty much the same thing. One thing to keep in mind, and this is just kind of some semantics here, but when we talk about something like NaCl, that formula, we really talk in terms of it's a formula unit. You're going to hear people tossing around, oh, it's a molecular compound, or you're forming a molecule of sodium chloride. You're not really forming a molecule of sodium chloride. Molecule implies covalent bond. This is going to be forming formula units. And so you can see in the picture there in that crystal structure where we've got Na+s surrounded by Cl-, and the Cl- are surrounded by the Na+. It's a well-organized and ordered system. It's going to be held together by those electrostatic attractions. So let's look at formation of ionic compounds. The main thing we're looking at here is when we form ionic compounds, we're trying to get a proper charge balance. We're trying to have an overall net charge of 0 on our compound. So if I look at sodium and I look at phosphate, sodium's a group 1 cation, it's going to form a +1 charge. Phosphate is a polyatomic anion, it's PO4 3-. So I've got a +1 and a 3-. What I'm going to do is I'm going to keep adding these together and adding more of them until my charge gets to 0. So when I have 1 sodium and 1 phosphate, my overall charge is a -2 because I have a +1 plus a -3. As I add another sodium, I go to Na2PO4. Well, now I've got a +2 and a -3. That's giving me a -1. I'm still not at 0. So I need to add a third sodium. Now I've got a +3 charge from my sodiums because I've got 3 of them, and I've got a -3 from my phosphate, so a +3 plus a -3 gives me an overall charge of 0. When I'm looking at formation of these ionic compounds, that's what I'm shooting for. I can't form a compound that has an overall charge. I always need that neutral compound whenever I'm looking at formation of these ionic compounds for naming purposes. Okay, so I'm always shooting for that overall charge of 0. Alright, so let's look at another example of this. If I combine Mg2+ and N3-, I want to know what formula am I going to form there. So I'm looking at combining Mg2+ and N3-. I want to know what formula is going to be formed. Right, but before we get into that, let's talk about what's actually happening here. So what's going to be the source of electrons in this? Well, the source is going to be that each magnesium atom, neutral atom, is going to lose 2 electrons. When that magnesium atom loses 2 electrons, what happens? It forms that cation, Mg2+. Okay, so we've got 2 electrons coming from each magnesium atom. Well, where are those electrons going to go to? Well, they're going to go to the nitrogen. Each neutral nitrogen atom is going to gain 3 electrons. That's why we get to the N3-. Okay, but keep in mind, the number of electrons lost must equal the number of electrons gained. The charges must balance. So if I have a single magnesium atom losing 2 electrons and a nitrogen atom gaining 3 electrons, those aren't equal, and I need to make them equal. All right, so let's look at how we can treat this. So, starting with 1 magnesium 2+, 1 N3-. Right now, if I look at those, I've got a +2 plus a -3, that's going to equal a -1. Well, if I were to write the formula for this, it'd be Mgn to the -1. That's not neutral. It still has a charge. So what do? Well, let's add 2 magnesiums to 1 nitrogen. Now I've got a +4 plus a -3. Now I've got a +1 charge. So I'd have Mg2n +1. But now I've got too much positive charge. Well, in order to balance out the positive charge, I can add another negative charge. So I've got +4 plus a -6 equals a -2. That's still not 0. My formula would be Mg2n2 to the -2. I've got too much negative charge. Well, how do I get rid of that extra negative charge? Add another cation. So if I add that third cation, now from the magnesiums, I have a +6 charge. From the nitrides, I have a -6 charge. +6 plus a -6 gives me an overall charge of 0. So my formula between Mg2+ and N3- is going to be Mg3N2. And keep in mind, the reason why I need 3 Mgs is because each Mg gives up 2 electrons. 3 of them combined together give up 6 total electrons. Where did all those 6 electrons go? Well, each nitrogen takes 3 electrons to get its 3- charge. So since each nitrogen has taken 3 electrons, I need 2 of those. That adds up to 6 electrons. Those electrons all came from the magnesium. All right, it's important that you understand that connection of where these electrons are coming from, where they're going to. All right, so let's now get into names of these things. When we talk about cations, cations are typically formed from a metal. So for main group metals, we just use the name of the element for their ions. So for example, lithium, Li, forms an Li+. The name of that would be the lithium ion. Now, we talked about this previously. You need to recognize the patterns here. That group 1 is going to form +1, group 2 is going to form +2, group 7 is going to form -1 ions. But we're going to focus on the cations, the positive ones first. And don't forget about the transition metals in the middle. They have multiple ones. Okay, so for example, chromium could be a +2, could be a +3. Well, because of that, we can't just use the name of the element, because if I just say chromium, we don't know whether it's +2 or +3. So the way around this is we use Roman numerals to indicate the charge of that ion. Chromium, parentheses Roman numeral 2, represents chromium +2. Chromium, parentheses Roman numeral 3, represents chromium 3+. That's how I know which particular cation I'm dealing with. You don't need to memorize all of these. Typically what you're going to be using this with is going to be the transition metals. Transition metals along with then tin and lead. Okay, those are the main ones you need to worry about. So when you see a transition metal, it's usually a safe bet to assume that you're going to have to use these Roman numerals. Now if you notice, it's got the older name listed there, where the lower charge has got the OUS ending, the higher charge has got the IC ending. You don't need to worry about those. So you don't need to know chromos and chromic. Okay, but you do need to be able to write out the other names. All right, so those are for the cations. Now let's look at the anions. So anions are going to be formed from nonmetals. They're going to be things that accept electrons, take a negative charge. All right, so here's a table of some common anions. Those are for common monoatomic anions. So with monoatomic anions, we're going to add an IDE ending to the base name. So Cl- is the chloride ion. Okay. O2- is the oxide. And you see examples there. But that's only going to be for the monoatomic anions. Problem is we're going to have something called polyatomic anions. Polyatomic meaning more than one atom. So if we look at a table of these, you can see some common ones here. And really for these common ones, you should really know the names and formulas for all of the 8 forms, the things that end in ATE. All right. There are a couple exceptions to that. You also need to know the OH minus, the CN minus, and the O2 2 minus. Those are hydroxide, cyanide, and peroxide. Those end in IBE, but they're not monoatomic ions. Okay, so those are some exceptions to that. Otherwise, though, you need to know the 8 form. One other thing that's on this list, even though it's not an anion, but it is an important polyatomic ion, is ammonium, NH4+. Well, because it's got a positive charge, that's actually a polyatomic cation that you'll sometimes see. So you need to know the name of that as well, and the formula. Now, when looking at these polyatomic ions, there's a lot of them there. And the reason why I say you only need to know the 8 forms, both the names and the formulas of those 8 forms, and when I say formulas, don't forget their charges. Okay, you need to know their charges as well. The reason for this, though, is that we have some rules, and if you know the 8 forms and you know these rules, you don't need to memorize all of them. You can predict all of these different formulas. So keep this table in mind. You may have to use it as a reference at some point, but you should really try to learn these formulas. All right, so let's look at some of these rules for these polyatomic anions. So if we have polyatomic anions that are going to contain oxygen, and they have more than 2 members in a series, we're going to use this prefix and suffix style of naming, right? And this is where I said if you know the 8 form. If we look at the root 8 form, that's the initial starting point. If you have that one memorized and you know the formula and the name for that, if you remove an oxygen from that 8 form, you go to the ite form. If you add an oxygen to the total number of oxygens in the formula but keep the same charge, you go to the perate form. If you remove 2 oxygens from that 8 form, you go to the hypoite form. All right, so I know that's confusing. That's why I'm going to show you an example right now. If I start and I memorize and know that chlorate, the chlorate ion is ClO3 with a -1 charge, if I know that form, and that's the only one I really need to memorize, if I subtract an oxygen from that formula, I go to the ite form, the ITE. So ClO3 -1 oxygen, keep the same charge, I go to ClO2 -1, that's the chloride. If I add an oxygen to that 8 form, I go to the perate form. So ClO3 -1, add 1 oxygen, I go to ClO4 -1, that becomes perchlorate. If I take 2 away from that 8 form, I go to ClO -1, that's going to be the hypoite form, so hypochlorite. So just from knowing that 8 form, I can then, using these rules, determine what the perate looks like, what the ite looks like, and what the hypoite looks like for these oxyanions. So instead of memorizing 4 things and 4 formulas, I memorize 1, apply these rules, and I'm good to go. Now keep in mind, this applies to anything that has an 8 associated with it. So when you have like the sulfate, the phosphate, the nitrate, okay, so these rules can help save a lot of time in memorizing a whole batch of different compounds. So learn how to use these rules. These particular rules also are going to apply to all the halogens. Chlorine's a halogen, so if I were to place all those chlorines with, let's say, a bromine, I'd get the perbromate, the bromate, the bromite, and the hypobromite, and that'd work with the iodine as well. Now let's look at another set of rules that are going to help us predict some names. If we have these polyatomic anions that contain oxygen and we add additional hydrogens, we've got a group of rules that we can use to predict those formulas and those names. But remember, you still at least need to know the formula and name for the 8 form. So if I have phosphate is PO43-, and I have that memorized, I know what it looks like and know its name, if I add 1 hydrogen to that, I get HPO4 2-. Well, because I added 1 hydrogen it becomes hydrogen phosphate ion, or sometimes known as biphosphate. If I add a second hydrogen on, now I've added 2 hydrogens, I now am at dihydrogen phosphate ion. If I add a third hydrogen to that, I get H3PO4 with no charge. Now keep in mind, we're talking about how to name anions. Anions are something that have a negative charge. So H3PO4 is no longer an ion. When I've added that many hydrogens, I've actually just made an acid, and I need to use the acid naming rules for that. So H3PO4 wouldn't be trihydrogen phosphate because it's neutral. Okay, so I only use this hydrogen and dihydrogen when I still have those charges. Okay, so we talked about naming cations, we talked about naming these anions. When we write out the name for an ionic compound, we always write the name of the cation first and then the anion. So for example, NaCl would be sodium chloride. Ionic compounds, because of all these rules we just went through, they're usually the most difficult to name. So if you can get these down, you're pretty much golden with the other ones. Because covalent compounds are fairly easy. Acid naming is going to follow similar rules to the ionic, but they're going to be slightly easier too. Okay, so these are kind of the tough ones. All right, so let's practice some of these.